Welcome back to the next video, everybody. Today we're going to be covering part 1 of proposition 4 of the general case of R equals T. And so let's get started. Okay, so we're going to keep the notation of all the previous few videos, so go review that if you haven't yet. We're going to let sigma prime be between a set sigma and sigma sub rho bar for our representation rho bar we've been working with recently. These are going to be finite sets of primes with certain properties. And we're going to denote by pi sub sigma prime the composition from the Hecke algebra T sub sigma prime to T sub sigma to O. And we're going to let eta sub sigma prime be pi sub sigma prime of the annihilator of the kernel of pi sub sigma prime. And it's easy to show this is a non-trivial object because T sub sigma prime is a reduced algebra. Okay. Let's let WP sigma prime denote the kernel of phi sigma prime. So kind of our R equals T map, compose this pi sub sigma prime. And recall from proposition 2 from, for example, video 11.6, that the cardinality of WP sigma prime over WP sigma prime squared is nothing but the cardinality of H1 sub sigma prime of Q add 0 row F tensor K mod O. Okay, although we haven't actually shown either one of these groups are finite yet. Okay. So here's the proposition. This is one of kind of the key propositions we're going to need to formulate a proof of R equals T in the general case. It says if sigma is in sigma prime is in sigma rho bar, and if F is in N sub sigma, and that's a new form with coefficients in O, then actually this congruence ideal, we call it, eta sub sigma prime, is contained in pi of the product of all the CPs over P in sigma prime minus sigma times eta sub sigma. So there's a strong relationship here then between eta sub sigma and eta sub sigma prime given by this relationship. Okay, this is a fairly hard result. So we're going to start proving it right now. But there's a really kind of a corollary we want to get out of this, which I'll call corollary CC, cohomology congruence. Given the above notation, the following is true. Okay, so the cardinality of H1 sub sigma prime of Q add 0 row F tensor K mod O divided by the cardinality of H1 sigma Q add 0 row F tensor K mod O is less than or equal to the cardinality of eta sub sigma over eta sub sigma prime. And so this side is kind of the cohomology side, and this side is the congruence side because these are called congruence ideals, okay? And I'll let you check that this is really just propositions 3 and 4 together, okay? We're going to begin the proof of proposition 4 by discussing symmetric square L functions. So as usual, K is the residue field of O with a residue characteristic, let's say L and odd prime. And rho bar from GQ to GL2 of K is a continuous, modular, irreducible, cyclotomic, semi-stable representation. For each prime P, we'll let alpha P of F and beta P of F denote the roots of x squared minus APFX plus delta P times P equals 0, where delta P is 0 if P divides NF, the level of F, and delta sub P equals 1 in any other case, okay? And so then the local L function at P of F comma S is just 1 minus alpha P F to P times P to the negative S, all inverse, times 1 minus beta sub P of F P to the negative S, all inverse, just by definition, okay? Now, if P equals L divides the conductor of rho bar divided by N sub F, then we will require that alpha sub L of F be the unit root in O. Okay, the symmetric square L function of F then is L sim squared of F comma S, and it's the product over primes P of L sub P of sim squared Fs, where what is this kind of local symmetric square L function? It's just 1 minus alpha squared sub P of F times P to the negative S inverse times 1 minus alpha sub P of F beta sub P of F P to the negative S inverse times 1 minus beta squared sub P of F P to the negative S inverse. Hopefully you can see the symmetry there and the squares there, so hence the name, right? It turns out this product converges on the real part of S bigger than 2 and has an analytic continuation, okay? Now we're going to start pushing towards computing this congruence ideal eta sub sigma, right? So we're going to let WP denote the kernel of the map pi from T sub sigma to O, from the kind of commutative triangle we've been working with, and we'll let I be its annihilator in T sub sigma. Since T sub sigma is reduced, WP intersect I is trivial, and WP plus I is a finite index in T sub sigma. We're also going to observe that O mod eta sub sigma is isomorphic to T sub sigma mod WP plus I. Okay, so we're now going to let L be a T sub sigma module, which is finitely generated and free over O, such that L tensor K is free of rank D over T sub sigma tensor K over O. We will also suppose that L is equipped with a perfect O bilinear pairing L cross L to O given by xy maps to bracket xy with the property that it's sort of self-adjoint with respect to t for all x and y in L and t in t sub sigma. Okay, giving such a pairing is really the same thing then as giving an isomorphism of t sub sigma modules L with O homomorphisms from L to O. And what is that isomorphism? It's just send x to bracket x comma dot. Okay, and so whenever we have a situation like this, we'll call L together with its pairing a self-dual t sub sigma module of rank D. All right. We're going to finish today just with a lemma that gives a lower bound on the cardinality of O mod eta sub sigma in terms of a basis x1 through xd for the free O module L bracket WP, which is the intersection over all x in WP of the kernels x from L to L. So you can view each x as a map from L to L and just intersect all the kernels. In other words, it's kind of an annihilator, right? And the lemma is called, I'll just call it lemma sub eta to the D sub sigma. And it just very simply says that eta to the D sub sigma is contained in O times the determinant of the matrix whose entries are given by bracket xi, bracket x sub j, where x sub I runs throughout this basis here, and so does x sub j. And then we have actually an equality if and only if L is free over T sub sigma. Okay, so we're just going to prove this today. Okay, so first we'll let L bracket WP and, first we'll notice that L bracket WP and L mod L bracket I are free of rank D over O. And the pairing kind of, bracket that we introduced earlier induces an isomorphism actually, L mod L bracket I with O homs from L bracket WP to O. The O module M, which is L mod L bracket WP sum L bracket I, is then certainly annihilated by eta sub sigma and generated by D elements. Moreover, M is isomorphic to O mod eta sub sigma to the D if L is free over T sub sigma. Okay, and all this is really to say that the cardinality of O mod eta sub sigma to the D is at least the cardinality of M with equality if L is free. But the cardinality of M is really just the same as the cardinality of the co-kernel of the natural map from L bracket WP into O homomorphisms from L bracket WP to O, arising from the bracket map. But this is really just the valuation of the determinant. This is kind of a standard linear algebra fact. Okay, but what is the valuation of the determinant in this case? Well, it's just the cardinality of O mod the determinant of that matrix that I was talking about a second ago by linear algebra. Okay, and so that establishes the proof of the lemma. And so we will use this then to go on and try to just push further into the proof of proposition 4 beginning next video. So I'll see you then, and thanks for watching.